Hi everyone, welcome to Foresight Space Group. We're really excited to have a few here on the call, and Ekaterina, our fellow, with us here today, including Kieran, who is hosting the group. And Ekaterina, today you'll be discussing how exoplanet discovery opens up a window into Earth's future. And without further ado, the stage is yours. Please take it away.
All right, thanks for the kind introduction. Happy to be here. For me, it's evening. For many of you, it's probably in the morning. Yeah, I wanted to share this nice little animation before we start, actually, because it's the sphere centered on the solar system that you can see in the middle with our couple of planets that we have. This is the 10 parsec sample, so that translates to something over 30 light years. And everything in red are small stars. There's a couple of bigger ones too. And every small green dot is a planet that we found in the last couple of decades. So that's to show there is a lot to look at in our immediate neighborhood. So yeah, I'm Ekaterina. I'm postdoc in the Netherlands. I study stars and exoplanets. And I'm going to tell you more about exciting things basically going on in my field and how that helps us potentially empirically study existential risks and our own future by proxy. All right. So basically, in far future, we want to have something like a permanent settlement on a planet outside the solar system, but there's a bunch of steps that we need to do before that. So could advance for a couple more steps. I think it's 4 or so. We got a bunch of things to do. We need to send the humans, send infrastructure, send exploratory probes. I think I have a couple more. We do need to do lots of engineering to get there. We need to select the planets, and then we need, in order to have something to select, we need criteria. So we need to characterize these planets. And even before that, as the last step, we need to detect these planets. And this is what my talk is going to be about. This is the very first steps of colonizing space, if you will. So that's my talk. 2 parts. First, we're going to talk about planet detection, and second, about planet characterization. If we wanted to go within the solar system, that's a different topic. I'm talking about extrasolar systems and planets outside the solar system.
Although the same work plan could be applied to places inside the solar system for that matter.
Yes. Yeah, but I'm not going to focus on the solar system in this talk because it's a totally separate matter with very different techniques, if you will. So I'm going to talk about planet detection and characterization. We have, as astronomers, all the same question: what is out there? And on the next slide, I show a bunch of questions that are increasingly complicated to ask and answer. The first question, of course, that has been around for quite a while: are there planets at all outside the solar system? That question is answered positively. We do. Then the next question: are there planets like Earth? This is an ongoing search. Then, well, we need to find them, figure out where they actually are, and whether they have the conditions suitable for life in terms of life as we know it, our own Earth-like biosphere. And they want to know if they are inhabited. And finally, if they are not inhabited, we want to figure out why, because that would be important for us to know. This is a whole lot of questions. So I want to quickly go through what I'm going to cover in the first part. I'm going to talk about exoplanet detection, and we're going to start with the first exoplanet detection, just for some context. Then we're going to look into exoplanet detection methods, cover 3 of them. Then we're going to take a look at the statistics where we are right now, and then briefly talk about second Earth searches and detections. All right. So first exoplanet is 51 Pegasi b, and it's a hot Jupiter. If we look at 51 Pegasi, this is a pretty normal star. I have some specs added in the next step. It's similar to Earth. It's about 50 light years away, so it's a G-dwarf, and it's roughly on the edge of what is visible to the naked eye. So if you advance a couple more steps, we see a nice picture of an artist's impression of what this could look like. It has half the mass of Jupiter, and it orbits its host star in only 4.2 days. That already tells me this is nothing we know from the solar system. The innermost planet of the solar system has an orbital period of 80 days. So this has already, from the start, been very surprising. The two authors, Michel Mayor and Didier Queloz, got a Nobel Prize for that a couple of years ago. That sort of kicked off the whole field of exoplanet science in 1995. It's not the first exoplanet detection, by the way. There's been some before that, but this is the first around a solar type star, which is why that is exciting. How did we find that planet? So I'm going to show a short video. This is showing the way radial velocity method works. You have two bodies orbiting each other. They bound to each other via gravitation. The center of the rotation is not the center of the star, even though it's pretty close to that. Here it's exaggerated, but it's offset from the center of the star, which makes the star wobble. And if you're not looking at the system like here, face on, but rather edge on, or close to edge on, you see the reflex motion. And when the star moves towards you, the light is bluer. If the star moves away from you, the light will appear redder. And so you see a nice curve of this. If you take spectra of a star over time, you see a nice curve that correspond to the planet's orbit. This has been the first detection method, and for the first decade or so, it has been the most productive. I want to show another one. So this, to me, is the coolest detection method. It's not the most productive, but it's direct imaging, where you basically just put a plate in front of your star and cover its light so that the contrast between star and planets, reflected light and intrinsic light, is reduced. And so you can see the planet directly. It is pretty hard to do because the star outshines the planet usually by a factor of 1 billion, at least. So this is only possible for a few select systems where the planets are relatively far out and fairly bright, which is typically the case for very young star planet systems. So if you move on to the next slide, this is, I think, the coolest video on the internet. It's 4 giant planets in wide orbits around a young star. So in the center, you see the covered image of the host star. And these pictures are taken over several years. So it's a long-term project. And over time, you can see the planets move in their orbits, and these are all gas giants that just recently have formed. We have about a couple dozen of such images so far, but I think this is the most long-term time series that we have. So this is pretty amazing. It would be nice if we could actually take pictures of exoplanets directly, but for the most cases, that is not possible yet. So these methods have been overtaken greatly by the transit method, which is the last one that I'm going to show you. So this method is also pretty simple to understand. It has a bit of a more restrictive requirement on how the star-planet system is oriented compared to the radial velocity method, as in the planet needs to go in front of the star. When it does, the light of the star is reduced for a brief period of time. So you see this little light curve in the bottom left. So you have a little transit shape, which tells you, among other things, the radius of that planet. And that will become important in a bit. So and this method has, since 2010-ish, been the most productive. So we talked about the first exoplanet, we talked about the exoplanet detections, we talked about all of those. Now onto the statistics and second Earth. This is our statistics so far, year of discovery versus the number of exoplanets discovered in that year. You see, it dates back to the late 1990s. Up until 2010, we've been painstakingly using the radial velocity method to find planets. We've been mostly finding these hot Jupiters because they're easiest to find with that method. And then in 2010, we launched Kepler, which was in operation between 2009 and 2018. And then in 2018, we launched TESS. Both of these missions are satellites sitting in space, staring at different patches on the sky. Kepler was staring at one particular patch on the sky, and TESS was an all-sky, still is, it's still operational, is an all-sky mission that just scans the entire sky and takes long term of light curves and just monitor stars for when they might have these dips. Overall, we found 5,500. I think that might be 5.6 at this point. There's more to come because we've been searching for an Earth-like planet, but so this is a video of the sun at relatively short wavelengths. Everything in that picture I do study, but on other stars. That is part of my work. The problem why we haven't found a second Earth, even though Kepler's pitch, its whole selling point was we are going to find a planet that is like Earth around a solar type star. The situation is that stellar activity, and that includes all the phenomena going on the star, so all these explosions, the bright spots, the dark spots, all these arcs that you see at the limb, all of those are magnetically driven phenomena that are pretty hard to understand if you can't resolve the object like you do with the sun. And even on the sun, it's hard. But we didn't understand stellar activity at the time good enough to figure out that it would be an issue. So stellar activity makes the star sort of flicker and adds noise to the light curve we want to detect the planet. And so the light curve looks more like this in this inset. And this is for a very quiet sun where we would actually detect one in the Kepler light setting. But unfortunately, most stars turn out to be more active. So they have more of these features and show them more often. That is the reason we found nothing, but there's hope. This is the statistics so far, but we now have a new mission that's going to launch at the end of 2026, and that is Plato. It's an ESA mission. You can see a nice picture of a prototype. I think it's the actual thing. At the moment, it's being rattle tested before launch, but things are seemingly going good enough for the envisioned date to hold. And its promise is that it's going to detect between 5,000 to 20,000 more planets in the course of its 4-year nominal mission. And one of the promises is that it will projectedly detect 10 to 30 planets that have a radius between 0.8 to 1.25 Earth radii in an orbit between 250 to 500 days around a sun-like star. So something like a G dwarf, something about 6,000 Kelvin hot. This is a projection. It might be only 5, it might be 100. Typically, astrophysics missions undersell what we're going to find. And this is only for the nominal mission. So if we continue searching, we might find more. But the upshot is we'll find something like an Earth analog by 2030. And that will only be the sort of the start of the journey. All right, I think that concludes section 2. So for 3 and 4, we have the summary. We have over 5,000 planets detected, with many more to be discovered. And the Plato mission is the one that's set out to find Earth analogs in the near future.
Katerina, I have a question before you move on. I was at Ames during Kepler and or much of it. And I thought that Kepler claimed that they had found Earth-sized planets in the Goldilocks zone. Now, of course, they don't know if they have the chemicals necessary for life as we know it. But could you address that? Didn't they claim they had found some Earth 2.0 candidates?
There are candidates, but for many of those, it has, in the early days of Kepler detection, there has been often claims of exoplanets that had later to be revoked. So it has been an exciting time. Every planet detection has been its own paper, and people have been scrabbling to publish that. So that has happened. That's one thing. The other thing is in the early days, particularly for those Earth-like candidates, we have been very uncertain about the radius, and many potentially Earth-like planets turned out to be small gas giants. So that has been an issue.
Thank you.
All right. Okay, so to move on from the first part to the second part, we've now covered planet detection. This is where we have what we have been working on for the past 30 years. And what we're now moving into is the actual planet characterization. So not only saying, yes, there is a planet, but also saying something about its properties. We want, ideally, what I hope for is to get empirical constraints on Earth's future. And that implies that we get empirical constraints on existential risks. And I'm a particular fan on the empirical constraints part because we have a whole lot of very good models, but nothing to calibrate them against except Earth itself and the solar system planets for which we know quite a lot. So this is the motivation to look into that more deeply, even if we don't want to colonize space in the very near future. We also want to secure our own existence. To give you a simple picture of what I mean by Earth's history and future, I think in billions of years, if we look at time after formation, we have this little timeline. We form after 10 million years, after the sun starts burning hydrogen. Planets are all done for the most part, and after 9 billion years, the sun explodes and takes the Earth with it, most likely. There's cases where planets survive, and we have found planets around dead stars, but we don't understand at all how that works. So this is our time frame. At this point now, 4.5 billion years in, we are already changing quite a lot of our Earth's properties. We're changing the composition of our atmosphere. All these things are already happening. In the past, at around 2.1 billion years, we had an oxygen boost from plants doing their thing. But in the future, we don't know. But we would very much like to know. I mentioned models, and I want to show you one recent one, which is in between being purely theoretical, because it's simulated observations talking about potential global catastrophes with permanent effects. A paper by Martin Schlecker from end of last year, and it looks into how runaway greenhouse would look like in a statistical sample of Earth analogs. The plot shows net installation. So to the left, you're closer to the star and it's getting hotter. If you're further right on the plot, it's cooler. And on the y-axis, you just see the radius. And I told you earlier, we get radius directly from the transit method. So this is pretty feasible, even though we haven't detected all the dots we need to have on that plot to actually find this runaway greenhouse threshold. They're assuming a bunch of things. I'm not going to go into detail with that. So this transition might look different, but from that it's just assuming natural causes, for instance. So if their model is correct, we would find this sort of step function. If something else is going on, for instance, anthropogenic climate change, we might find a different situation. So this is all theory, but in order to put any sort of constraints or calibrations on that, we need to characterize a planet. So ideally, we want a comparison sample of siblings. If you move on to steps.
Hey, Ekaterina, I don't mean to get in. You can just deflect this question if you don't want to go down this rabbit hole. But as I posted in the chat, how do you square the idea that we're changing the atmosphere and there's a potential of a runaway greenhouse effect with the fact that there have been times in the history of the Earth when CO2 was 8 times the current level and the planet was still teeming with life?
I think I'm going to deflect the question because I'm not going into climate change research in detail. I'm just entertaining, like, we can talk about a different form of catastrophe. And sure, even though if Earth heats up by 8 degrees and we don't turn into Venus and instead we have a completely different climate, we can discuss that scenario instead and how that would show up in difference in radius. That's totally fine by me. Another scenario would be that's probably not too likely for Earth, but would be interesting for other planets, would be looking into how volcanism on different planets affects the radii it might end up with. For many planets, might end up with a runaway ice house, which Earth hasn't had an episode of, having being pretty cold. I don't mean that this is the main example. I'm just meaning that this is a very tangible thing. Yeah, we can talk about that more afterwards. So one of the key things, if we want to look into our own future, is to know how old the planet that we're looking at is. For ourselves, we know how old the system is. We can age date ourselves. But for other stars, I want to say, difficult. And I want to go a little bit into that because it's pretty important. If we don't know if the dead or alive planet is younger or older than us, it doesn't tell us anything about, have we already passed this bottleneck or this great filter or whatever and survived to this point, or is this dead planet in our future? Okay, so we move on to the next step. So this is the first figure you will see whenever you study astronomy for the first time. This is the first plot people will show you. So you have temperature on the x-axis, luminosity on the y-axis. So how bright the star is and how hot it is. The colors supposed to represent the temperatures. And if you move 2 steps, there's 2 regions in this Hertzsprung-Russell diagram. One is the big stars, the blue stars basically, which are extremely unstable. They form and they basically immediately explode within a few million years. This is for astrophysical timescales, that's immediately. And then on the other side, there's extremely stable stars, of which the sun is actually on the short side. Sun-like stars and red dwarfs, the ones that like AB Dor is shown down at bottom, those live 10 times, 100 times longer. We don't know because they live longer than the universe is old at this point. And these are extremely stable. So to understand how we tell the ages of stars, we need to combine these unstable and stable stars in one sample. And this is how it works. So the next step is, it's hard, but we've been doing that for over 100 years now. So we have some strategies. The first strategy is open clusters, and the second strategy is stellar rotation. To understand how we use stellar rotation, we need to understand open clusters first. So you need to understand 2 things. First, an open cluster is a group of stars that formed at the same time. There's been one cloud, it collapsed, something happened, and you form stars of all masses. You form a few of these unstable giants, and you form a whole lot of these stable small stars. And you can tell the age of that group of stars. I'm showing one, the Pleiades on the left here is a nice picture, by the shape of their Hertzsprung-Russell diagram. So if you move on 1 step, this is the Hertzsprung-Russell diagram of this particular group of stars. You see in red all the background stars for comparison, and you can identify the stars that belong to the Pleiades because they're spatially bound and they move together. And this cluster is 120 million years old. We can tell that because we have a good idea of how stars evolve, particularly the big ones on these timescales. We see a slightly older cluster, and what happens in that, I want you to note the biggest stars in that distribution. So I've told you they form and they basically immediately explode, or explode very quickly, and the smaller they are, the longer it takes them. So these stars tell me, okay, if these stars of these masses are evolving off the main sequence, becoming giants and explode in supernova, etc., the cluster must be this age. So this is how we've been telling ages of open clusters for quite a while. The problem is not every star is in an open cluster. In fact, most stars are not. So we need a new method. That brings us to the next slide. Now we need to look at stellar rotation, and that has been around since the 70s, but only recently with actually Kepler and TESS we have been getting really good at it. In this figure, I show you, again, temperature of a star, hot stars on the left, like red dim stars on the right, the sun at 6,000 Kelvin, and on the y-axis now we have rotation period. If you move on 2 steps, again, you recognize the Pleiades and Praesepe, the clusters that I've shown you before. We use them as benchmarks to see how rotation period can actually say something about age. And it does so very well for sun-like stars in particular. If you draw a vertical line above 6,000 Kelvin, that in the Pleiades, you would expect a certain rotation period. If you're 1 billion years old, you would expect a slightly slower rotation period. So this plot is pretty complicated, but we're in the process of building the appropriate models to actually use rotation to tell the age of the star. So I think I have another step that just shows the general thrust of it. Old stars rotate slower than young stars, and
Ekaterina, can I ask a clarifying question here?
Yeah.
So in order to use this data to, you've colored these by their age, but you can't be circular. You might have to have an independent estimate of the age. Is that not correct? And is that from the HR diagram? Or how do you decide that these certain stars are 6 billion years old and other stars are 1 billion years old?
Yeah, so all of the stars in that figure belong to these open clusters. So for them, we have an independent measurement via the Hertzsprung-Russell diagram.
Okay, thank you.
And then we use those stars as a benchmark so that now we can translate what we see here to say, if I meet in the wild a star that seems to have the same temperature as the sun, rotates at, I don't know, 10 days or so, oh, it looks like it must be around 1 billion years old. That's
okay,
rough.
but couldn't you do the same thing by just, if you could form a mass estimate of the star and you have the mass and the temperature, the color, or whatever the HR shows, you could also get an age estimate that way?
Technically, yes. Unfortunately, for stars that are like the sun or smaller, they don't move at all until they become red giants. So they just sit there. They don't move along the main sequence. This is why we need in open clusters the big stars and how they turn off and become giants. Yeah, but otherwise we could technically use open clusters for small and calibrate it directly on the mass. But unfortunately, this gives you uncertainties of several billion years for any given star, and that's practically useless. So we talked about the age, and now we want to assume we have figured out how old this is. We find a planet that is teeming with life or practically dead. We want to know that and figure out what there is in the atmosphere, if there is one, what we can see. And we actually know the age at this point, so we can tell this has been, similar to how Earth had been in the past, or, oh, this must be a planet that is older than us, that has went through evolutionary steps that are yet to come for us, perhaps. All right, so this is my last part here, the actual properties. And this is, telling age was hard. Telling planetary properties is new and hard, because we've only started looking at exoplanets a couple of years ago and really constrain their properties. Okay, yes, so I want to talk about two categories. One is mass and radius, and the other one is atmospheres. Let's move on to the first one. Okay, this is my favorite star-planet system. It's not a sun-like star. It's actually the smallest star that can exist. It's an M8 dwarf, so it's not even 3000 Kelvin hot. It's half as warm as the sun. But it has 7 terrestrial planets, and 3 of those are in the habitable zone. It's called the TRAPPIST-1 system. And just for comparison, if you move on another slide, this whole system is teeny tiny. It fits entirely into the orbit of Mercury. I think the outermost planet has an orbit of a couple dozen days. So it all fits very neatly together. In these stars are one of the most common out there. So you could imagine that this is a pretty common occurrence. So people have been very excited about this system, and it's actually one of the best characterized because the star is so dim and so small. Both the radial velocity and the transit contrast has been high enough to very well constrain both radius and mass. So if we go to the next slide and advance a couple of steps. Yes, yeah, that one too much. Okay, perfect, thank you. So we can use mass and radius to constrain what the planet is made of. Because if we have mass and radius, we can tell the bulk density. And if you look at this diagonal, you see all the planets with their respective letters from B closest and H farthest out, and also the solar system planets, the terrestrial ones, except for Mercury, because that's too small. And there's different models with what we know, and the blobs around the different planets give you like 1 sigma and 2 sigma uncertainties. You can exclude a planet with lots of water in the atmosphere. This is already impossible. Some planets can, especially I think G, is compatible with some water in the atmosphere. People produce models of lots of surface water worlds. This is pretty compatible. Then there's more models I'm not going to go into details of. And then you see the solar system composition, where, of course, Earth and Venus and Mars fall pretty directly on. All I want to show you here is this is the best we got so far. We can't even tell a water world apart from solar system composition which has very little water comparably.
So does this mean that TRAPPIST-1F is the best candidate?
It doesn't mean much at the moment, but from this, I think best candidate in terms of habitability, I assume. Yeah, we're going to talk about habitability in a second. I think I'm not going to go to F. I think it has not yet been observed in transmission spectroscopy, but we'll come to that. All I want to say here, this is how, from just mass and radius can say something, even though at this point, 2021, it's not much.
Ekaterina, you mind if I ask a quick question?
Yeah, sure.
What does this figure assume in terms of, if anything, about tidal locking or lack of it? Do you know?
Not sure if they include it in the method, but they assume that the planets will be. So I'm pretty sure that if it needs to be considered in these models, they assume that they are tidally locked.
Got it. All right, thanks.
Because the system is supposedly 7 billion years old at this point. Okay, I'm not sure how much time we have left. I still want to come to the last part of this talk, which is arguably the most exciting because it answers the question: is there a similar composition to Earth's on, for example, the TRAPPIST-1 planets? Even though this is not a solar type star yet, this is the best we got in terms of contrast. Let's look into how we characterize atmospheres at this stage of the field. We do that with transmission spectroscopy, and put simply, there's a nice sketch that NASA made. NASA made so many good illustrations. It's gonna appear slowly. Yes. All right. So put very simply, you go in transit. Fortunately, all the TRAPPIST planets are transiting, and compare the spectrum of the star to the spectrum of the star with the planet in transit. What happens during transit is part of the light is blocked by the planetary body, and part of it is blocked by, not entirely blocked, by the thin annulus of the planetary atmosphere. And so some of the light moves through that atmosphere, and some of it is absorbed. And by the difference between just star and star with planet, you can tell what was absorbed in the atmosphere, and tell what the composition of the planetary atmosphere was. Okay, if we move, right. So this is one application of this that is very straightforward and pretty impressive. If you look at a planetary transit in broadband visible light, like optical light, the transit will look pretty symmetrical if you move one step. We move, a circle moves in the front of another circle, and then it moves away from that circle. You get a symmetric shape. But what we see, if we look into just hydrogen, is nothing like you would expect from an orderly atmosphere. And what that shows us is that this atmosphere is just catastrophically evaporating from that planet because the star is blowing it away. We have actually a few systems that do that, and the next slide shows a nice picture of that. This GJ436b. It's not an Earth-like planet. It shouldn't have a hydrogen atmosphere if it was Earth-like, right? It's rather a Neptune-sized thing. But some of these planets might be precursors of future Earth-like planets. So this ties into the concept of when you start out with a hydrogen atmosphere and then it's blown away, like you see here. When it's gone, you start outgassing a secondary atmosphere that is more like the Earth's. Perhaps the question remains how that one survives, but that's a topic for discussion. All right. Now, we have launched the James Webb Space Telescope not too long ago, and we had great success looking at gas giant planets in their atmospheres. We have, again, with transmission spectroscopy, infrared light curves. We can see all sorts of features. We can see that there's water, there's CO2, there's all sorts of things. The models fit quite well. There's still a couple of discrepancies, but we're moving on to understanding at least Jupiter-like planets. We're trying to do the same for the TRAPPIST-1 planets and actually detect an Earth-like atmosphere. We have already observed TRAPPIST-1b. So this was a headline. Innermost TRAPPIST-1 exoplanet is hot and airless. It's pretty sure it has no atmosphere. We tried to do TRAPPIST-1c. as it stands, it might have a little bit of CO2, but it's just something we can't exclude, but we detect nothing. It's just the non-detection is compatible with having a little bit of an atmosphere left. And I don't know what happened to D, but we're definitely observing E. And we finished observing that. So this is the observing schedule for TRAPPIST-1e. It has been completed end of October last year. They're probably just working very hard on analyzing the data, and I expect the results to come out in the course of the upcoming months. So stay tuned for TRAPPIST-1e, but as it stands, we have not detected an Earth-like atmosphere at this point. So I have to disappoint you here. Okay, so the main takeaways, to me, timelines for interstellar space colonization are unclear, but to me, it seems a good idea to find and characterize potential destinations. We're finding exoplanets quite quickly, and we're looking forward to detecting an Earth-like planet in the next couple of years. If we have a sample of Earth siblings, we can, and I hope I've motivated that enough, look into the future and past of our own planet. And that will hopefully, and the field is moving in that direction, empirically constrain probability of extinction, catastrophes, and other events that have permanent effects or long-lasting effects on the planet. I hope you find exoplanet characterization now more exciting than you already hopefully did. There's a lot to discover and to stay on the news because JWST is going to detect a whole lot of interesting things. Thank you so much for staying with the complicated technical setup.
So much for totally rocking it. That was really fun, I think, to be side mastering through all of this. It definitely, I think, makes you
thank you so much.
understand everything a lot more. Thank you so much for joining. I know we're at time now, but if you want to drop your email in the chat, I'm sure people have lots of questions, comments. I already see someone sharing related research. And so I'm sure that is not the final words. And I'm hoping that we get you in person for our space workshop this fall, and then we can hopefully touch back on many of the bits that you discussed already. But this is absolutely stunning and really exciting, especially for
looking
what's ahead in
forward
the next few
to
years.
get in touch with many of you.
Thank you so much. That was quite the blast. I'm now pretty excited, and hopefully we can constrain the X-vis part of Earth as well a little bit to that workshop, to that research. Thank you everyone for joining. That was wonderful. Thanks a lot, Ekaterina. Hope you have a wonderful rest of your day.
Thanks for hosting.
Bye-bye.
Bye everyone.